Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to talk on module Multipole Fields Part 1 under the paper Electromagnetic Theory. So after completing this module, the students will be able to understand spherical harmonic expansion of vector fields, particularly useful for the study of multipole radiation from localized sources, scalar wave equation and its spherical wave solutions, detailed study of spherical harmonics, angular momentum operator and the angular functions, transverse electric and transverse magnetic solutions of the electromagnetic field. Let us see what is scalar wave equations. Spherical harmonic expansion was extensively used in the undergraduate course for solutions of problems of electrostatics, particularly boundary value problems involving certain symmetries. For time-varying phenomenon, it is useful to study spherical harmonic expansion of vector fields. This is particularly used for the study of multipole radiation from the localized source. We now look at such vector multipole fields. Let us begin with the spherical wave equation of the scalar wave equation before we study the vector wave equation. Let the scalar field xi xt satisfy the homogeneous scalar wave equation where delta square xi xt minus 1 divided by c square del square xi by del t square equals to 0. Now we try to solve this equation by using the Fourier transform method. We define the Fourier transform of xi xt in time as xi xt equals to integral from minus infinity to infinity xi x omega e raised to power minus I omega t d omega. So that xi x omega equals to 1 divided by 2 pi integral minus infinity to plus infinity xi xt into e raised to power I omega t dt. Xi x omega satisfy the Helmholtz equation, that is del square plus omega square by c square xi x omega equals to 0. It is very often convenient to find the solution of the Helmholtz equation or wave equation in coordinates other than the Cartesian coordinates, in particular for systems possessing spherical symmetry about some point which can conveniently be taken to be the origin. So solution in terms of spherical coordinate is more appropriate. We use the spherical polar coordinate representation of the Laplacian operator, that is del square equals to 1 divided by r into del square by del r square of r dot plus 1 divided by r square sine theta into del by del theta of sine theta into del by del theta dot plus 1 by r square sine square theta del square by del phi square dot, where dot represents the function on which it acts. Using this form for the Laplace operator, we get 1 by r del square by del r square of r dot plus 1 divided by r square sine theta into del by del theta of sine theta del by del theta of dot plus 1 by r square sine square theta del square by del phi square dot plus k square whole into xi dependent on r theta phi omega equals to 0, where k is equals to omega by c. Now students, let us study about the spherical harmonics. So solve the equation by the usual method of separation of variables. So in this direction we write xi dependent on r theta phi omega as xi r theta phi omega equals to capital R as a function of r, capital Y as function of theta and phi. So on substituting this, we get two independent equations, that is 1 divided by capital R d by dr of r square into d by dr of capital R plus k square equals to lambda, and 1 by y into 1 by sine theta into del by del theta of sine theta into del by del theta of y plus 1 divided by y into 1 divided by sine square theta into del square by del phi square of y equals to minus lambda, where lambda is a constant independent of the coordinates. The second equation can further simplified by assuming solution of the form y theta phi equals to capital theta dependent on theta and capital phi dependent on phi. Applying the method of separation of variable once again, we can get second equation as 1 divided by capital phi into d square by d phi square of capital phi equals to minus m square, and lambda sine square theta plus sine theta by capital theta into d by d theta of sine theta d by d theta of capital theta equals to m square. On substituting the above equations, we find that the Fourier component xi as function of x omega satisfies the Helmholtz equation, that is del square plus omega square by c square into xi as function of x omega equals to 0. It is very often convenient to find the solution of Helmholtz equation or wave equation in coordinates other than Cartesian coordinates. In particular, for systems possessing spherical symmetry about some points which can conveniently be taken to be the origin, solutions in terms of spherical coordinates is more appropriate. We use the spherical polar coordinate representation of the Laplacian operator, that is del square equals to 1 divided by r into del square by del r square of r dot plus 1 divided by r square sine theta into del by del theta of sine theta del by del theta of dot plus 1 divided by r square sine square theta del square by del phi square of dot. These angular solutions are a product of trigonometric functions, here represented as a complex exponential and associated Legendre polynomials y, L, m, theta, phi is equals to n e raised to power I m phi into p L m cos theta. Several different normalizations are in common use for the Laplace spherical harmonic functions. We use the standard convention regarding associated Legendre polynomial, that is PLM as a function of x equals to minus 1 raised to power m into 1 minus x square whole raised to power m by 2 into dm by dxm of PLX, and PL minus m as a function of x equals to minus 1 raised to power m into L minus m factorial divided by L plus m factorial whole into PLM as a function of x. The Laplace spherical harmonics are generally defined as YLM as a function of theta and phi is equals to under root of 2L plus 1 into L minus m factorial whole divided by 4 pi into L plus m factorial and whole into PLM cos theta into e raised to power I m phi. Then it follows y L minus n theta phi is equals to minus 1 raised to power m YLM star theta phi. The normalization and the orthogonality condition on the spherical harmonics are integral y L dash M dash star theta phi into YLM theta phi d omega is equals to integral from 0 to 2 pi d phi into integral 0 to pi sin theta d theta into y L dash M dash star theta phi into y L M theta phi equals to delta L L dash into delta M M dash. So using these spherical harmonics, the desired solution is xi dependent on x omega is equals to summation from L equals to 0 to infinity into summation M equals to minus L to L of FLR into YLM theta phi. The radial function satisfy the equation, so we get d square by dr square plus 2 by r into d by dr plus k square minus L into L plus 1 by r square whole into F1r is equals to 0. Now we make the substitution of F1r is equals to r raised to power minus half ULR and obtain the following equation for ULR as d square by dr square plus 1 by r into d by dr plus k square minus L plus half raised to power 2 divided by r square whole into ULR equals to 0. Now this is nothing but the well-known Bessel's equation. D square y by dx square plus 1 by x dy by dx plus 1 minus v square by x square into y x equals to 0. So here the parameter v is equals to plus half and x equals to kr. Now this is nothing but the well-known Bessel's equation, which has the solution in terms of Bessel function as j L plus half as a function of kr and j minus L plus half as a function of kr. So j Vx equals to x by 2 raised to power v into summation j equals to 0 to infinity of minus 1 raised to power j divided by j factorial into gamma function of j plus v plus 1 into x by 2 raised to power 2j and j minus vx equals to x by 2 raised to power minus v into summation from j equals to 0 to infinity of minus 1 raised to power j divided by j factorial into gamma function of j minus v plus 1 whole into x by 2 raised to power 2j. For integer v, the two solutions are linearly dependent. So j minus nx equals to minus 1 raised to power n into j minus nx. The two solutions that are always linearly independent are jvx and the Newman function or Bessel function of the second kind. Nv as a function of x equals to jv as a function of x into cos v pi minus j minus v as a function of x whole divided by sin v pi. So which implies that fl as a function of r equals to a divided by r raised to power half whole into jl plus half as a function of kr plus b divided by r raised to power half into nl plus half as a function of kr. For half odd integer order, define instead spherical Bessel function and spherical Hankel functions. JLx equals to pi by 2x whole raised to power half into jl plus half as a function of x. NLx equals to pi by 2x whole raised to power half NL plus half as a function of x. HL12 as a function of x equals to pi by 2x raised to power half whole into JLx plus or minus iota NLx. JLx equals to minus x raised to power L into 1 by x d by dx whole L times of sin x by x, and NLx equals to minus x raised to power L into 1 by x d by dx L times of cos x by x. The small and the large argument limits of the spherical Bessel function are for x very much less than 1, JLx tends to x raised to power L divided by 1 into 3 dash dash up to 2L plus 1 whole into 1 minus x square divided by 2 into 2L plus 3 up to n times. Similarly, NLx tends to 1 into 3 dot dot up to 2L minus 1 divided by x raised to power L plus 1 whole into 1 minus x square divided by 2 into 1 minus 2L and so on. For x very much greater than 1, we have JLx tends to 1 by x sin x minus L pi by 2, NLx tends to minus 1 by x cos x minus L pi by 2, and HL12 x tends to plus minus iota raised to power L plus 1 into e raised to power plus minus iota x by x. So combining all these, we get xi x equals to summation from L equals to 0 to infinity into summation from m equals to minus L to plus L of ALM1 HL1 as a function of kr plus ALM2 HL2 as a function of kr whole into YLM theta phi. The coefficient ALM1 and ALM2 are arbitrary and determined from the boundary conditions, where m is again some constant. A priori, m is a complex constant, but because of phi must be a single valued. Phi plus 2n pi is equals to phi as function of phi. Phi must be periodic function of phi. So m is necessarily an integer and phi is a linear combination of complex exponentials e raised to power plus minus im phi. The solution function y as function of theta phi is a regular at the poles of the sphere where theta is equals to 0 or pi. Imposing this regularity in the solution theta of a second equation at the boundary points of the domain is a Sturm-Liouville problem that forces the parameter lambda to be of the form lambda equals to L into L plus 1 for some non-negative integers with L greater than equals to mod of m. Furthermore, a change of variable to transform this equation into the associated Legendre equation solution is a multipole of the associated Legendre polynomial, that is PLM cos theta. For a given value of L where there are two L plus 1 independent solutions of this form, one of the integer m with minus L less than equals to m, less than equals to L. 1 by sine theta del by del theta of sine theta del by del theta plus 1 divided by sine square theta del square by del phi square plus L into L plus 1 whole into YLM theta phi equals to 0. So in quantum mechanics, this operator is associated with the orbital angular momentum. So we define the differential operator L equals to minus iota times R cross del. Then in quantum mechanics, orbital angular momentum is h cross L. On using the operator del in spherical polar coordinates, we can easily verify that L square equals to minus 1 divided by sine theta into del by del theta of sine theta del by del theta plus 1 divided by sine square theta del square by del phi square, where L square is equals to L dot L equals to Lx square plus Ly square plus Lz square. So here L square YLM theta phi is equals to L into L plus 1 into YLM theta phi. So here L into L plus 1 are eigenvalues of the differential operator L square, which in quantum mechanics is related to the angular momentum. So instead of the Cartesian components, the more convenient combination is L plus equals to Lx plus iota Ly equals to e raised to power I phi into del by del theta plus I cot theta del by del phi. Similarly, L minus equals to Lx minus iota Ly equals to e raised to power minus I phi into minus del by del theta plus iota cot theta del by del phi, and Lz equals to minus iota del by del phi. We have the relations R dot L equals to 0 and Lm minus YLM equals to under root of L minus plus M into L plus minus M plus 1 whole into Y Lm plus minus 1, and LZYLM equals to MYLM, and the commutation relations L square into L vector equals to L vector into L square, and L vector cross L vector equals to iota L vector, and Lj del square is equals to del square Lj. Now let us see the angular functions. So far we have concentrated on the radial functions for the scalar wave equations. We now re-look at the angular functions and introduce some concepts of use in the study of the vector wave equation. The basic angular functions are the spherical harmonics, that is YLN as function of theta and phi, which are the solutions of the second of equation, that is 1 divided by sine theta del by del theta of sine theta into del by del theta plus 1 divided by sine square theta into del square by del phi square plus L into L plus 1 into Y Lm theta phi is equals to 0. In quantum mechanics, this operator is associated with the orbital angular momentum. So in vacuum, the source free Maxwell's equations are del dot E vector equals to 0, del cross H vector equals to epsilon naught del E vector by del T, del cross E vector plus mu naught del H vector by del T equals to 0, del dot H vector equals to 0. So assuming a time dependence of the form e raised to power minus I omega t equals to e raised to power minus I ck t, so middle equation becomes del cross H vector equals to minus I k by z naught into E vector, del cross E vector equals to I k z naught h vector, and z naught here is equals to under root of mu naught by epsilon naught or equals to mu naught c. On taking curl of the equation and using the above equation, so on taking the curl, we get curl of del cross h vector equals to del into del dot h vector minus del square h equals to minus I k by z naught into del cross e vector equals to k square h vector, and del square plus k square into h vector is equals to 0 and del dot h vector equals to 0. E vector is equals to iota z naught by k into del cross h vector. Similarly, del square plus k square whole into E vector equals to 0, del dot E vector equals to 0, and H vector is equals to minus iota 1 divided by z naught k whole into del cross E vector. Either of the two sets of equation is completely equivalent to the Maxwell's equation. So now del square into r dot E vector is equals to E dot del square r vector plus 2 into del dot E vector plus r vector dot del square E vector equals to r vector dot del square E vector equals to minus k square r vector dot E vector, and this implies that del square plus k square whole into r vector dot E vector is equals to 0. Exactly similarly, we can prove del square plus k square into r vector dot h vector is equals to 0. So this implies that r vector dot E vector and r vector dot h vector satisfy the scalar Helmholtz equation. We now define a magnetic multipole field of order Lm in the following way. R vector dot h vector Lm raised to power capital M equals to L into L plus 1 whole divided by K into GL as a function of KR into YLM function of theta phi, and R vector dot E vector Lm raised to power capital M equals to 0, where GL as a function of KR is equals to AL1 HL1 KR plus AL2 HL2 KR. Now R dot H can be related to the electric field by equation R vector dot H vector is equals to minus I 1 divided by Z naught K into R vector dot del cross E vector equals to minus I 1 divided by Z naught K into R vector cross del vector into dot product with E vector equals to 1 divided by Z naught K into L vector dot E vector. L vector dot E vector equals to Z naught KR into R vector dot H vector, which implies that L vector dot E vector Lm raised to power M R theta phi equals to L into L plus 1 Z naught GL as function of KR YLM function of theta phi, and R vector dot E vector Lm raised to power M equals to 0. The operator L vector acts only on the angular variables, which implies that radial dependence on E vector is given by GL KR. L vector acting on YLM can be best changed the value of M and L remains invariant. So this implies that component of E vector can be linear combination of various L, M, R fixed, which implies of E vector can be linear combination of various Lm for a fixed L, which must be equal to the value of L on the right hand side of the equation. E vector Lm raised to power m function of r theta phi must be such a linear combination of y Lms for various m such that L vector dot E vector Lm raised to power m r theta phi involves only a single value of m. L vector dot L vector is the only scalar operator under which y Lms are invariant. Now L square y Lm theta phi equals to L into L plus 1 y Lm theta phi, which implies that E Lm raised to power m r theta phi equals to z naught g L k r into L vector y Lm theta phi. Now because these electric fields are transfers to the radius vector, these fields are often called transverse electric rather than magnetic multiple fields. In an identical manner, we define fields of the electric pole of order Lm by r vector dot E vector Lm raised to power e equals to minus z naught L into L plus 1 divided by k into Fl kr into y Lm theta phi, and r vector dot H vector Lm raised to power e equals to 0. Following exactly the same procedure as for the transverse electric fields, we get H vector Lm raised to power e dependent on r theta phi equals to Fl kr into L vector into y Lm theta phi, and E vector Lm raised to power e equals to iota z naught by k into del cross H vector Lm e. Now let us study about the multipole expansion of the electromagnetic field. Whatever we have done so far has been in the context of scalar fields and scalar wave equations obeyed by the scalar field. The electromagnetic fields, that is E vector and H vector, it is more customary to deal with the magnetic field H vector rather than the magnetic induction field vector B, and we have to now develop the corresponding formalism for such fields. The normalized form of vector spherical harmonics L vector into y Lm theta phi, we get x Lm vector theta phi equals to 1 divided by under root of L into L plus 1 whole into L vector into y Lm theta phi, where L is not equals to 0 and x naught theta phi equals to 0, and integral of x vector L dash m dash star into x vector Lm d omega equals to del L dash into del m dash, and integral x vector L dash m dash star dot product with r vector cross x vector Lm d omega equals to 0. When both types of fields are present simultaneously, the total electric and magnetic field is the sum of two terms, and the general solution of the Maxwell's equation is H vector equals to summation Lm bracket Ae as a function of Lm into Fl kr capital X vector Lm minus iota by k into Am function of Lm into del cross Gl function of kr into X vector Lm bracket close, and E vector equals to Z naught summation over Lm of bracket start Am function of Lm into Gl function of kr into X vector Lm plus iota by k into AE LM into del cross F1 function of kr into x vector Lm. The coefficient AE Lm and AM Lm and the constants appearing in FLKR and GLKR are determined by the sources and the boundary conditions. Now R vector dot H vector equals to summation from Lm over Am as a function of Ln into under root of L into L plus 1 whole divided by K into GL KR into YLM theta phi. And on using the orthonormality of spherical harmonics, we get integral y L dash M dash star into R vector dot H vector d omega equals to summation Lm into Am function of Lm into under root of L into L plus 1 whole divided by K into GL KR into integral y L dash M dash star into y L M d omega equals to Am function of L dash M dash into under root of L dash into L dash plus 1 whole divided by K into GL dash function of KR, or Am function of Lm into GL function of KR equals to K divided by under root of L into L plus 1 into integral YLM star into R vector dot H vector into d omega. Similarly, AE function of Lm into FL function of KR equals to minus K divided by Z naught into under root of L into L plus 1 whole into integral YLM star into R vector dot E vector to d omega. The two sets, magnetic multipole and the electric multipole, together form a complete set of solution to Maxwell's equation in a source-free region. Though the terminology TE and TM is often used for these fields, the terminology magnetic multipole and electric multipole is preferable, since the source of the two types of radiation, as we shall see later, are the magnetic moment density and the electric charge density respectively. So students, let us now summarize what we have learnt in this module. In this module, we have considered the multipole expansion of the electromagnetic field, which is particularly useful for the study of multipole radiation from localized sources. We first revisit the scalar wave equation and its spherical wave solutions. Next, we present a detailed study of spherical harmonics. We then go over to the study of angular momentum operator and the angular functions with which we are quite familiar from quantum mechanics. Finally, we have obtained the transverse electric and transverse magnetic solutions of the electromagnetic field. Thank you.